Hello, everyone. This is an overview of the angle resolved photoemission spectroscopy, or ARPES technique, and this is one of the techniques used in my group. This is intended to be a general overview of the technique. It does not cover many of the modifications and variations of this technique that have shown up in the past decade. It's just intended to be a starting point. So as far as prerequisites for understanding this, I think that knowledge about momentum space and the free electron gas and modifications thereof is the proper starting point. So if you haven't watched the mini lecture or read the notes on that, that's the third mini lecture. That might be a good idea before delving into this. So this is an outline of what I'll talk about. So I'll do a very brief review about what's in momentum space and why we want to study there, general principles of ARPES, looking at simple data. Then I'll get into a little bit of the formalism. So I'll go a little bit quickly here, emphasizing sort of which aspects which I should say, which terminology I want you to remember from this and which consequences I want you to remember. So this is the part that'll be most technical, but also the one that is the least needed to get started. Then I'll discuss a little bit about instrumentation, other aspects of the experiments, such as energy and momentum resolution and temperature. And finally, I'll show some examples of data. And this is not intended to be sort of an exhaustive list in any sense. It's just a couple of examples where I can highlight different attributes of what shows up in data. All right. So, um, I want to, at this point, sort of disambiguate something that a lot of students get confused about, and that is crystal momentum versus momentum transfer. And to illustrate the difference, I'm showing different data on the same system. And this system is a copper 111 Fermi surface. So you take the surface of copper 111, not Fermi surface, it's the copper 111 surface. So the first graph is the Fermi surface. So copper, it happens to follow a free electron gas picture fairly well. So if you have a two-dimensional picture thereof, the Fermi surface is just a circle. And this is half of the Fermi surface, so it's half a circle. So the second image is an STM image that shows what are called Friedel oscillations. So this is one consequence of the wave-like nature of electrons, and it's actually visualizing the wave-like nature of electrons in some sense. So the idea is that you have electrons that are waves of some given wavelength, which is inversely related to the momentum. And then they see another wave and they interfere with one another. And these patterns that look like ripples in a pond, these are actually interference patterns. And the period of this interference pattern is set by twice the Fermi momentum. So basically kf is the radius of the circle, and you have the highest probability of scattering or interference if you have two electrons located at the Fermi energy with momentum kf, in momentum and magnitude rather kf, but in any direction, interfering with one another. So the periodicity of this interference pattern, it has length to kf, and usually q, or momentum transfer, is the terminology that is used to describe this interference process. So another thing that you can measure in a copper 111 surface is just the the lattice, and that is what is shown here. So this is a low energy electron diffraction or lead pattern of a copper 111 surface. So it has sort of the triangular symmetry of that plane of copper. You're missing the central dot because of this shadowing. And basically from the direct lattice, you can have the reciprocal lattice, which is discussed in the second mini lecture. So with this slide, I just want to disambiguate the concept of crystal momentum, which is the space that we are in for ARPES measurements, versus momentum transfer, which is something that STM experiments can measure, versus the reciprocal lattice, which is a related concept as was discussed in the mini lecture 3, but it is relating to the structure of the atoms rather than the wave-like electrons. Okay, so in momentum space, there are some phenomena that all materials have and some phenomena that some materials have. So all materials have Brillouin zones, all metals have Fermi surfaces, and all materials have band dispersions. So then beyond that, there are phenomena that are sort of material specific that can also be measured by ARPES. So this includes charge density wave gaps, superconducting gaps, spin density wave gaps, electron boson coupling, heavy fermion hybridization gaps, spin momentum locking, surface states. The list goes on and on. So there are many structures in momentum space that can be measured directly by ARPES, and this technique gives very detailed information about how electrons move in a crystalline solid in momentum space, which in turn can be mapped onto either sort of emergent phenomena such as superconductivity, or it can be mapped onto bulk measurements such as transport. Okay, so the overview of the technique is here. So the purpose is to measure electronic band dispersion, so energy versus K. And to do this, the technique uses the photoelectric effect plus conservation laws. So the photoelectric effect is when you shine light on a sample, it emits electrons. So it turns out that those electrons that get photoemitted are still carrying information about how they were moving back inside the crystalline solid. And that is what is measured by ARPES. So what ARPES actually measures is the kinetic energy of electrons that are photoemitted after shining UV light on them, and the angle with which they are photoemitted. So that is what we measure. We measure kinetic energy and we measure emission angle using a photoelectron analyzer. And then there are some conservation laws that are shown here. So for energy, the kinetic energy that we measure is related to the binding energy. That's the energy relative to the Fermi energy that the electron had back inside the crystalline solid. And the relation there just involves the photon energy, which you know, and the work function, which you either know or measure. And then the other equation is the conservation law for momentum. So the crystal momentum is related to the measured quantity of the emission angle via square root of 2 times the free electron mass times the kinetic energy of the electrons. All right, so these two simple equations basically govern what we measure and what we want. We want energy versus momentum. We want dispersion relations. So what is actually being measured by ARPES is a little bit more complicated. I shouldn't say complicated, I should say a little bit more information rich. So it turns out that in a real material, you have some interactions that in the mini lectures that I've given have been ignored. So So you have electrons interacting with other electrons, you have electrons interacting with lattice vibrations, you can have electrons interacting with magnetic degrees of freedom. So all of this can happen. And these interactions can change the band dispersion, they can change energy versus K, and they can also change the lifetime of so-called quasiparticles. So in a free electron gas, which was in mini lecture 2, the electrons are fundamental particles and they live an infinitely long time. In a crystalline solid, electrons, uh, 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 or I should say, one thinks of rather than sort of infinitely long lived electrons, one thinks of quasi-particles that are sort of electrons and interactions that might have some finite lifetime. So anyway, the single particle spectral function, which is what is measured by ARPES, captures both band structure and interactions. So this is what the equation for the single particle spectral function looks like. So it has a number of components. It has the bare band, which is just energy versus K. And this is how electrons would move around if there were no interactions. But there are interactions, and the interactions are captured in the self energy, which has the real part and the imaginary part that are Kramers-Kronig related to one another. And the real part of the self energy tells you how interactions affect band position. So, for example, how they make a band flatter, how they introduce wiggles into a band. And the imaginary part tells you how these interactions affect the line width or the lifetime. So ARPES measures both band structure and interactions, and it does it all at the same time. So it's very difficult to tease out the original band structure from the effect that interactions had on it. Typically, you measure all of it together, and you have to interpret all of it together. All right. So at this point, let's go ahead and look at some simple ARPES data. So this is for a simple metal. It's a copper 111 surface state. So you've seen a portion of these data already. And it's very interesting because, so this is an experiment from 2013, so fairly recent. But it is still, measuring things that were in the mini lecture number 3 and measuring them quite similar to what was presented in the lecture. So let me walk you through these data. So the x-axis here is the crystal momentum in the plane. So in the photoemission process, you conserve momentum in the plane. For momentum out of the plane, it's a little bit more complicated. I'm not sure I'll talk about it in this lecture, but there are ways to get information about out of plane momentum. But in any case, the x-axis here is momentum in the plane, and specifically crystal momentum. The y-axis is the electron binding energy. So reference to a couple of slides ago, this y-axis is the binding energy whose absolute value is equal to the energy minus the Fermi energy. So the 0 represents the Fermi energy, or more precisely, the chemical potential. So I mentioned in the third mini lecture that the Fermi energy is strictly a 0 temperature quantity, and at elevated temperature you use the chemical potential. However, it is the norm in this field to write the y-axis as energy minus the Fermi energy, energy relative to the Fermi energy, and this is just directly taken from a published paper, and most papers label their axis like this. So that is the y-axis. You'll notice, well, actually, before I do that, I should mention that the momentum here is along some trajectory in momentum space. And in this case, it is what is called a high symmetry cut that goes through the origin of kx and ky space. And points A and B here corresponds to point A and B on this Fermi surface. So this figure that I just popped in, the axes are kx or ky on the vertical axis and kx on the x-axis, and this half circle represents half of a free electron gas because the other half is just going to look exactly the same. On this graph, there are sort of two different pieces, and one of the circles looks a little thinner. The thinner one was taken with a laser light source that has better resolution and much smaller spot size. So it's sort of splicing two different experiments together. All right. So the orange regions here and the bright regions in general, visually to you, it probably looks like a parabola, and indeed it is a parabola. So this material just happens to have energy versus K that is very similar to the free electron picture. So energy is equal to h bar squared K squared divided by 2 times the effective mass. And then finally, you'll notice that above zero, so for positive binding energy, there is nothing there, and that is because of the Fermi-Dirac cutoff. So basically, the Fermi function tells you that for energies smaller than the Fermi energy, you will have occupied states. For energies larger than the Fermi energy, you'll have unoccupied states, and that is precisely what we see. So with ARPES experiments, if you measure, for instance, the polycrystalline sample, you can see the Fermi function directly. And you can also, when you raise the temperature, you can see the step function getting rounded. So it's a nice illustration of fundamental concepts in solid state physics and statistical mechanics. Alrighty. So yeah, so this is a Fermi surface map, and it is usually produced by taking sort of adjacent slices. So for instance, adjacent vertical slices, how this was probably done, and pasting them together. So nowadays, it's not always done like that anymore, but you can think of this map as being constructed that way. So um, there are other things to notice in these data if one zooms in more closely. And that illustrates the fact that ARPES is such an information-rich technique that you can study a material that's been studied before. And if you just look in a different regime, if you do something different to it, if you just look more carefully, you can sometimes discover new things. And indeed, that is what is seen here. So there are a couple of aspects that I'll point out. So what I'm showing on the next slide is basically this square right here, just zooming in. So zooming in close to the Fermi energy where the action really takes place. And there are a couple of things to see here. So first of all, you'll notice that there's two bands, not just one. So that is something that is well understood. So this is an effect of spin orbit coupling. This is called Rashba splitting. So basically, the two bands here represent two spin states, and it was quite surprising that this was observed. Not that it was observed, but that it was actually measurable, because this is copper. Copper is a fairly lightweight atom, and Rashba splitting tends to get larger as the atoms get heavier. So, for example, if one were to measure gold instead of copper, one would see a much larger Rashba splitting. So that is one thing. But another thing is that there are these wiggles. So the dispersion, the energy versus K is not monotonic. It sort of has a little bend, which is quantified here. So the y-axis here are the real part of the self-energy and the imaginary part of the self-energy. And they attribute these wiggles in the energy versus K dispersion relation to electron phonon coupling. So this is an example of how ARPES, although it's a technique that ostensibly measures electrons, it can get information about behavior in the lattice as well if the lattice excitations couple strongly to electrons. So in this case, there is a phonon mode that couples strongly to electrons and causes sort of a bend or a kink in the band dispersion that is readily visualized with ARPES. All right, so that was an example of data that on the surface looked just like very simple textbook mini lecture 3 about electrons. But if you look more carefully, there was more to it. So now I want to get into a little bit of formalism about ARPES. And portions of this discussion are going to be a little bit technical. And the technical bits, I'm going to skip over them quite a bit because the intent for the purposes of this lecture is just for you to become familiar with some of the relevant vocabulary and some of the relevant phenomena. So if you want to have more information at the end, I'm going to have some resources that you can look into. Okay, so we're going to go back to the beginning and think about the photoemission process. And the photoemission process is modeled using a three-step model, and the three steps are as follows. So the first step is optical excitation of electrons in the bulk. The second step is travel of the excited electrons to the surface. And then the third step is escape of the photoelectrons into the vacuum. So the photoemission intensity is given by the product of these three processes and then some other stuff. With this graph, I just want to illustrate that steps 1, 2, and 3 are of decreasing mathematical complexity, but um, uh, uh, um, steps, but the importance is kind of a non-monotonic function, where I would say step 2 is the one that is most consequential for ARPES experiments, and steps 1 and 3 are somewhat less important. Okay, so let's begin with step 1. So step 1 is optical excitation of an electron in a bulk. So as a reminder of the photoemission process, you have UV light hitting the sample, and then that light is absorbed by electrons. And in step 1, those electrons are promoted to some higher energy level. So, um, the start, the electron is in an occupied state of some n electron wave function, which is called psi sub I superscript capital N. And at the end of this step, the electron is in some unoccupied state of this same n electron wave function. And an important approximation is what is called the sudden approximation, and that approximation is that there's no interaction between this photoelectron. So once an electron gets hit by a photon and something happens to it, it's called a photoelectron, and the electron that it's left behind. So the probability of this transition, so going from the start wave function to the end function, is related to Fermi's golden rule, where importantly, you have a matrix element that involves the electron momentum and the vector potential of the photon. So then the next step is to express the final wave function as a product of one electron states and an n-1 electron state. So that electron that got excited, it's about to exit this crystalline solid. So that's why we sort of separate it out from the pack, and we consider it as a one electron wave function multiplying the n-1 electron final state wave function. And then this curly A just means that this is some fermionic wave function that is properly anti-symmetrized. All right. So then with that approximation, the matrix element term gets slightly rewritten, where you have a matrix element term involving only single electron wave functions, and then another product state of n-1 electron wave functions. So the first term that involves the single electron wave function, initial and final states, and this A dot P, that is what is called the ARPES matrix elements. And the one thing that I want to get out of you were to remember out of these slides, and I'll come back to that a little bit later when we actually look at data, is that there is an ARPES matrix elements term, and this is where it comes from. And what this actually is these are experimental details which affect the measured intensity. So experimental details are things like your experimental geometry, like which way is the beam coming in relative to the sample. It is things like the polarization of light. It is things like the photon energy of the light. And different choices will sort of make the intensity of the spectrum you measure look different. So this is something that can be exploited, especially at a synchrotron light source, where you can control the photon energy to, for instance, pick a photon energy where the electrons in this material emit the brightest. It can also be used to choose experimental conditions where one band is more prominent than another band. So ARPES matrix element terms, they can be sort of something that is just an incidental nuisance, or it can be used as sort of a way to control the data quality. But what I really want you to get from this slide is that there are some experimental details which affect the measured intensity, and where this comes in is in the first step of the photoemission process. All right. So the next step of the photoemission process is the travel of the excited electron to the surface of the material. So basically, the light has some penetration depth into the material, and this penetration depth. Oh, that's what I'll be uncovering. All right. So sorry, these slides were originally from a class where there was a little bit more participation in terms of this information. So let me just uncover what the answers are. All right, so photon energies that are typically used in photoemission experiments are something like 6 to 6,000 eV. In this lecture, I'm primarily considering a sort of the lower end of this range, so 6 to 150 electron volts. And that is primarily where my group works as well. So let's take some number in this range, let's like 20 eV, and how deep does this light penetrate into a material? So this answer is going to have a little bit of material variation, but it's generally going to be the same. And it's on the order of 11 nanometers for this frequency of light, and copper as the material. So 11 nanometers is 110 angstrom. It's not bulk, but it's a good depth into the material. It is many units. So the next question is, what is the electron inelastic mean free path of electrons that have a kinetic energy of 20 eV? So that is, how far can an electron travel before scattering into something? So that is about zero point 0.6 nanometers. And the copper unit cell is around 0.36 nanometers. So for this specific scenario that has been described, basically you have your light that is exciting electrons into a depth 11 nanometers into the copper. And then those photoelectrons, when they move, they will typically bump into something every zero point 0.6 nanometers. So because of this, it's really only the photoelectrons that are created within 0.6 nanometers of the surface that can actually get to the surface before they scatter and escape. So once they scatter, they lose their momentum information and they're no longer good for ARPES. So it's because of this second step that ARPES is a really surface sensitive technique, which is where a lot of the technical difficulties, technical meaning, operational difficulties of this experiment arise. So, and an additional consequence of this short inelastic mean free path of electrons that have this energy is that the photoelectrons that are emitted primarily originate from the first two unit cells. So so everything that I've been discussing, but expanded, is summarized in this so-called universal curve. So the y-axis here is the electron inelastic mean free path. So how far electrons go before bumping into something, which tells you sort of the depth starting from the surface where one can extract a photoelectron. So the x-axis is energy. It's kinetic energy of the electrons. You can also view it as the photon energy of the light, because at this point the electrons are still in the material, so they haven't lost a work function worth of energy yet. So this is called a universal curve. It's cited a whole lot in ARPES literature. And you can see that it sort of has a check mark shape where at low photon energy, you start to get larger mean free path. And then at higher photon energy, you also start to get a larger mean free path. So the data points here are a compilation of many materials, which is why it's called a universal curve. So usually when we discuss electron mean free path, we just use sort of the line on this universal curve. We don't consider materials differences because they're sort of secondary to differences between different energies. All right, so in my research and also this mini lecture, we are sort of in this range of photon energies indicated by the green bar. All right. So the conclusion of step 2 of the photoemission process is that the electron mean free path determines how deep into the sample ARPES studies. And if we want to get more bulk sensitivity, we can go to lower photon energy, which becomes problematic because you are limited by the work function of the system you're using. Or you can go to higher photon energy. So hard X-ray ARPES is a more surface sensitive measurement, a more surface sensitive version of the technique. There are trade-offs, however, in terms of energy and momentum resolution. All right. So this slide, I'm going to go I don't want to go into it in detail, but basically in ARPES, there's always been a question, so it's a surface sensitive technique. Is what you're measuring relevant to the bulk? So there are several answers to this question. One answer is that there are many interesting systems that are actually two-dimensional, so that question is a little bit irrelevant. So one example is something that we've seen already. So the surface state on copper 111 is a strictly two-dimensional state. There are many examples of quasi two-dimensional materials, so graphene, tungsten, selenide, all of these 2D exfoliatable materials that electronically are quasi two-dimensional. So there, the distinction between surface and bulk is also a little bit less important. And additionally, one can often study model layers of those systems where they are strictly two-dimensional. So, um, so another thing that I'll say about this issue of surface versus bulk that doesn't get into the content of this slide at all is that the double check that we often have is that in solid state physics, there's very rarely a single experiment that tells you all the answers. So typically you need a suite of different experimental techniques to really understand a given system. So oftentimes there will be some information from ARPES where taken that alone, you would not have certainty whether you are getting information that's relevant to the bulk of the material. However, there are other techniques that are bulk sensitive, and if they give sort of equivalent or agreeable information, then you have support for the fact that what is measured by ARPES on that specific material is relevant to the bulk. In other cases, you might find that the surface is quite distinct from the bulk, and there are many materials where that is actually an asset. So many materials, specifically topological quantum materials, have distinct surface and bulk states that define their unique and interesting properties. And the fact that you can specifically measure the surface state is a strong attribute of this technique. All right, so Let me go on to step three now of the photoemission process, and that is sort of what you typically think of photoemission. So this is the escape of photoelectrons into the vacuum. So at this step, the electron will lose a work function worth of energy, and you have some transmission probability through the surface, which depends on energy of excited electrons and also the work function. So just because an electron makes it to the surface without scattering, there's not 100% chance that it will actually be photoemitted. Okay, so that is the third step of the photoemission process. Um, and and with that, we have the basis for considering some aspects of the ARPES instrumentation. So in this portion, I'll get into the light sources, the spectrometer, and the vacuum. All right. So generally, an ARPES system, and at this, so I made this lecture before I had my own lab. I should probably put my own lab here. But in any case, the elements of an ARPES experiment are you have some electron analyzer, you have some analysis chamber. That's where the sample sits to get its electrons photoemitted. And you have some sample manipulator, which is the thing that the sample sits on. This allows it to move into the measurement position and also allows it to be rotated. And what else? And you have a light source, which is very important. So the photon source, I'm not sure where it is in this image actually, but I'll get into what types of light sources can be used. So that is the general setup. And inside these stainless steel containers, it is ultra high vacuum. And a lot of the technical difficulty in managing and setting up an ARPES system is really achieving this ultra high vacuum. All right, so let's begin with the light sources. And there are a number of light sources that are used in ARPES experiments, and they have their advantages and disadvantages. So one type of light source is a laser, and we have one of these in my lab at 6EV. So typically, laser light sources operate between 6 to 11 eV, and this statement is certainly true for quasi continuous wave laser light sources. Nowadays, there is what is called HHG or high harmonic generation laser light sources. So these are typically, or they are always pulsed light sources that can go up to higher photon energy. So laser light sources can be quite monochromatic. Very small energy bandwidth of the light source. They don't have to be, and if they're a pulse light source, they're typically not. They can often be quite intense, and their polarization can be controlled. Another type of light source, which is also typically used in lab-based systems, including my own, is a gas discharge lamp. So here, basically, you have some typically noble gas. You create a plasma out of it, and then you extract some light out of the plasma. And if you employ a monochromator, the bandwidth can be quite small with this sort of light source. The intensity, however, can sometimes be low, and the polarization is always random. So this can be a good or bad thing. So in modern experiments, often you do want to control the polarization. So in that sense, it is a bad thing. But if you control polarization, sometimes in some portions of the Berlin zone or some portions of your Fermi surface, you have weakened intensity. So random polarizations can sometimes mitigate against that and have uniform intensity everywhere. And finally, there are synchrotron light sources. And the advantage of a synchrotron, the major advantage is that the photon energy is variable. So different synchrotrons and different end stations at different synchrotrons typically specialize in different energy ranges. So one might be tuned to operate best between 20 and 200 eV. And another one might be tuned to operate best between 7 and 30 eV. It just depends on a given synchrotron and a given end station. So these synchrotron light sources can be made relatively monochromatic, but there is a trade-off. So basically, there's a trade-off between bandwidth and intensity. So in a synchrotron, you start off with white light and you use some sort of diffraction grating to pick out what frequency you want specifically, and then the bandwidth is then chosen by manipulating a slit to cut down the bandwidth. And cutting down the bandwidth is directly consequential to reducing the intensity. So oftentimes there's plenty of intensity to work with, and this isn't a big trade-off. Sometimes you do have to make a trade-off in the how fast you do your experiment versus how good the energy resolution from the light source is. Um, so um, the synchrotrons, they have fixed polarization, but they have several choices typically of fixed polarization. So most synchrotrons will allow linear vertical, linear horizontal, left circular, and right circular. So it's not full variability of polarization typically, but it is some opportunity to choose a polarization. All right. So, moving on to the business end of an ARPES instrument, this is the ARPES spectrometer or analyzer. So, there are two general types of analyzers. There's a hemispherical, which is the one that is used in my lab, and it's also the one that's used in most synchrotrons around the world that have ARPES end station. The other type of light source is a time of flight analyzer, which is less common. So for that reason, let me go through that one first. So the time of flight analyzer, it requires a pulsed light source because the way that it discriminates different energies of photoelectrons is basically which one reaches the detector first. So as the name implies, time of flight is how energy discrimination is done. So additionally, this type of analyzer has three-dimensional detection of electrons all at once. So basically it measures kx, ky, and ky, and also the energy as a function of time of flight. So it's three-dimensional detection automatically. So the more common light source is, or rather the more common analyzer is a hemispherical analyzer, which uses concentric hemispheres kept at different potentials to differentiate different energies of electrons. So basically, it's like a capacitor, a parallel plate capacitor. So if in a parallel plate capacitor, if you have an electron between my hands, sorry, I don't have three hands, the electron will get deflected to one of the plates, but then with the hemispherical analyzer, the plate curves to follow where the electron would get deflected. So anyway, a hemispherical analyzer as a default has two-dimensional detection of electrons. So basically, there is a slit in the analyzer, the entrance slit right here, that selects some one-dimensional trajectory in momentum space. Uh, um, so you detect energy versus K in two dimensions. So K along that one-dimensional trajectory is mapped out in position along this slit. And however, there is new-ish, not super new, but new-ish technology called a deflector, which essentially allows to collect three-dimensional data by deflecting the trajectory relative of electrons relative to the slit without moving the sample itself. So, um, hemispherical analyzer is by far the more common implementation of ARPES instrumentation, at least at this point in time. And here are photos of both of these types of analyzers. So another aspect of ARPES experiments is ultra-high vacuum. And the need for ultra-high vacuum is twofold. So first of all, these experiments are trying to measure electrons. So you want to get electrons from the sample to the analyzer before they bump into something. Actually, you don't need to just get it to the analyzer, you need to get it all the way through the detector, through to the detector. So that is one reason why it needs vacuum. But the more critical reason is the small electron mean free path that makes it only sensitive to the first couple of unit cells in a material. So basically, if you have poorer vacuum, you'll have atoms absorbing or sticking onto the surface. And once they create a monolayer, that is another layer of atoms that photoelectrons need to go through before they can be photoemitted. So just to illustrate this difference, so high vacuum is considered to be between 1 to the minus 3 to 1 to the minus 9 torr, and ultra high vacuum is considered to be between 1 to the minus 9 and 1 to the minus 12 torr. So as a reminder, atmosphere is 760 torr. So the molecular mean free path, so that's how far an atom travels before bumping into another atom. If you have high vacuum, is 10 centimeters to 100 kilometers. So at 1 times 10 to the minus 9 torr, an atom will travel 9 kilometers before it is likely to bump into another atom. So clearly, these vacuum chambers much shorter than 1,000 kilometers. So in ultra high vacuum, you go orders of magnitude higher. So 10 to the minus 12 torr corresponds to the molecular mean free path of 100,000 kilometers. Okay, so relevant to ARPES experiments, we want to know for a given pressure, how much time is needed to deposit a monolayer on the sample surface. So once you have a monolayer of atoms on the surface, then your photoemission experiment becomes much more difficult because you have this extra layer that electrons might scatter in before being photoemitted. So in high vacuum, you'll get a monolayer within an hour and a half. So 1 times 10 to the minus 9 torr, an hour and a half. And mid-range here is something like a couple of seconds. So with this amount of vacuum, you will get a monolayer way before you can actually take a measurement. But with ultra high vacuum, you can have an hour and a half up to 2 months. And a typical estimate is about 20 hours. So in an ARPES experiment, typically, depending on the vacuum of the chamber, we find that typical samples can be measured on the order of 24 to 48 hours. And at some point, either the sample will do some aging due to some photochemistry, or you'll get a monolayer. But usually, what will happen is a combination of both. So this is why ultra high vacuum is needed. It's needed to protect the surface of the sample. And apropos to that, before we do the measurement, we need to create an atomically clean surface. And there are several ways to do this. So one way is cleaving in situ. And that is what my group typically does. So cleaving in situ, you have your sample on top of some sample post, and then on top of that, you glue a ceramic post. And then you come in with something that might look like a screwdriver. It's a wobble stick. It is something that sits inside ultra high vacuum, but it can be operated from the outside. Knock off your top post, and then you're left with a clean surface. Relating to this, there are some synchrotron end stations where there is glove box access, so you can achieve a clean surface via mechanical exfoliation. So that's one method. Another method is growing a material in situ. So you have some sort of molecular beam epitaxy or pulse laser deposition growth chamber that's attached to the ARPES chamber. You grow in the growth chamber, and then without breaking vacuum, you move into the ARPES chamber. And then finally, sputter and anneal is another way of achieving a clean surface. So basically, you put a material into the vacuum chamber that might have some impurities on the surface, and you come in with a sputtering gun, which basically shoots typically high energy argon at the sample, and that can knock off some of the impurities, also some of the atoms you want as well. And then you can heat it up or anneal to get the atoms you want back into their righteous position. So these are some of the ways that you can achieve an atomically clean surface without exposing your sample to air. All right, so we're almost done here. Let me now discuss some other miscellaneous aspects of the experiment. So first, I want to discuss resolution. So as I mentioned at the beginning, what we want to measure is the single particle spectral function, which contains information about band structure and interactions. This is subjected to the Fermi-Dirac cutoff, which is fine. I'll come back to that in a little bit. There's the prefactor here, that's the matrix element terms. So that is from the first step of the photoemission process, and it tells you how experimental details affect your intensity. And then all of this stuff is convolved with a resolution ellipsoid in energy and momentum. So this resolution will essentially broaden out your spectrum relative to what is actually being exhibited by your material. So what is measured in an experiment is all of this. So the resolution is included on top of that. So energy resolution, the origins of this type of broadening come from several sources. So one is the light source bandwidth. So that is something that I discussed a few slides ago. Another aspect is electrical noise. So typically, if you want to really get the best resolution that you can in terms of energy, you need to do some extra grounding of your system. And then finally, there is the attribute of the spectrometer. So there is something called the pass energy, which when you do ARPES experiments, it's going to be one of the parameters that you control in your data collection software. So typically there are certain choices that are given, 0 0.5, 1, 2, 5, 10 EV, and it goes further up. So typically with higher photon energies, you'll end up using higher pass energy. So what the pass energy actually is it is this equation, and ultimately it is related to the potential difference between the two plates of your hemispherical analyzer. And then in the denominator, it has some term that involves the radii of your two hemispheres. So then the energy resolution is related to the pass energy via this equation, where W is the width of the entrance slit. So that is also something that you can control in the experiment. And then R naught is the average radius of the analyzer. So basically, R1 and R2 are the inner and the outer radius, and then their average is the average radius. So it's typically something like 20 centimeters. And then alpha is the angular resolution. And this is also something that is an attribute of the analyzer. And this is something that is quoted in the machine specs, and it can be as small as 0.05 degrees. So basically, this equation relates the energy resolution to various attributes of both the spectrum of the spectrometer, some of which are fixed, such as the radius, and some of which are controllable in an experiment, such as the pass energy and the entrance slit width, but also energy resolution. It can come from electrical noise and light source. So the spectrometer is only a portion of the puzzle. So the momentum resolution is a little bit more straightforward. The momentum resolution just comes from the second conservation law, where momentum is related to the sine of the emission angle. So if you, and it's also related to the kinetic energy of the photoelectrons. So if you take the derivative of both sides, you get the momentum resolution is related to the angular resolution, which is what was called alpha on the previous slide. That's a property of the spectrometer. It has the cosine of the emission angle, and then it has the square root of the kinetic energy. So if you want to make momentum resolution smaller, there are several ways to do this. So one is to use lower photon energy. And this is a big advantage of low photon energy. Another way to do this is to go to higher angles where the cosine of the emission angle is smaller. So What this means in practice is the lowest emission angle, you access the first Brillouin zone, but in the second Brillouin zone, there is equivalent information. So if you measure in the second Brillouin zone, you're at higher K and you're at higher emission angle, and the cosine is going to be smaller, so your momentum resolution is going to be smaller there as well. Let's see. Okay, and I should also mention that another aspect of momentum resolution that doesn't directly relate to this formula is the fact that photons carry momentum that is proportional. So photon momentum is equal to the photon energy divided by the speed of light, and and basically light can provide a momentum kick to electrons, which essentially scrambles some of their momentum information. So decreasing the photon energy also decreases this momentum kick, and it increases the momentum resolution that way. So that is separate from this formula. Okay. So the last thing that I want to so something else that I want to mention uh, is uh, is the first set of data that I showed, this copper 111. And I mentioned that this Fermi surface map, it has sort of two data sets spliced on top of each other, and these data sets are actually taken with two different light sources. So the one that looks broader and fuzzier is taken with a helium lamp, so helium 1 alpha, and the one that is sharper is taken with a laser, and a laser with 6.05 eV. So B is sharper than A for several reasons. So first of all, the energy resolution of the laser in this specific experiment happens to be better. The momentum resolution of the low photon energy is always better. And something that's not obvious just by looking at the numbers here is that the laser was actually taken with a tiny spot size, and this can be used to avoid averaging over sample inhomogeneities. So that is another advantage of laser and synchrotron light sources as opposed to gas discharge lamps, that they can be focused to a small spot. All right, so a couple of notes on resolution. So instrument resolution represents a convolution of the original spectrum with a resolution ellipsoid. It does not represent the smallest feature in energy or momentum that can be resolved. Resolution can also move spectral features around a little bit because it is a convolution. And sometimes better resolution is not the be all end all. So sometimes there are trade-offs to achieving better resolution that are necessary trade-offs, and resolution has improved a lot in the last 30 years. So what is standard nowadays was very much state of the art 20 years ago. All right, so temperature. So temperature comes into ARPES data via the Fermi-Dirac cutoff and via changes to the spectrum. So this is a little illustration showing the Fermi-Dirac function at different temperatures, and at higher temperature, it becomes a more rounded step function. So the Fermi-Dirac cutoff gets broader at higher temperature, which actually can be a good thing. It gives access to more unoccupied states. However, there is a trade-off for this, and that is that spectra get broader at higher temperature. And this is generally not so bad in ARPES experiments as it is in, for example, STM experiments, but physics introduces thermal broadening when you raise the temperature. So just to ground yourself in what is generally achieved in ARPES experiments as far as temperature. So ARPES experiments, usually they have a flow cryostat, which means you don't have a sample sitting in a bath of liquid helium or liquid nitrogen. You have gas flowing through the system, and then the sample is sort of thermally connected to some cold finger, which has very good thermal conductivity. So typically in an ARPES experiment, they usually don't go to very high temperature. Typically 400 Kelvin is the maximum. There's some end stations that are different. And the minimum temperature is as follows. So 20 Kelvin is sort of a standard minimum temperature that many synchrotron and lab-based light sources achieve. 7 Kelvin or so is fairly standard as well if you have a little bit of radiation shielding to improve that spec. And there are some systems that can get down to 1 Kelvin, although I should say that at this point in time, this is still quite rare. And in fact, in the United States, there are no synchrotron end stations that I'm aware of that do achieve 1 Kelvin. There are some around the world that do this. Okay, so this brings me to the very last bit. And this is just looking at some data. And learning how to look at ARPA's data is kind of an ongoing process. And this is not intended to be the full training. It's just a couple of small examples that will just illustrate some aspects of looking at ARPA's data. Okay, so these are some data on graphene, and graphene, if you recall, it's supposed to have a Dirac-like or light-like dispersion. So these data were collected actually quite a long time ago nowadays, and the way that the graphene was produced is differently from how it's usually done in ARPES experiments nowadays. So nowadays in ARPES experiments, there are ways to mechanically exfoliate graphene the usual way. But back in this day, that was a little bit trickier to incorporate with an ARPES experiment. So the way that graphene was actually created was a trick that was found. You basically take silicon carbide and you cut it on a specific angle, and then you heat it up. And when you heat it up, the silicon evaporates, leaving behind carbon, and you end up with graphene. You actually end up with several layers that are fairly decoupled from one another. So in this work, I want to illustrate two ways of slicing up ARPES data. So one way of slicing up ARPES data, you sit at constant momentum and look at intensity as a function of energy. So this is called an energy distribution curve, or EDC, and that is what is shown here in this panel that is right below the words EDC. So you can see that there's this gray bar, and this indicates that well, the gray bar doesn't indicate anything, but if you look at the EDC, you can see that there's a peak at higher binding energy, a peak at lower binding energy. Lower binding energy means closer to zero. And then those peaks never quite meet. There's always a gap between them. And this is indeed a gap in the graphene surface state. The other way of slicing up ARPES data is the orthogonal way. You sit at constant energy and look at intensity as a function of momentum. This is called a momentum distribution curve, or MDC, and that is what's shown in the panel below the word MDC. So basically, in the MDC, you can also see the opening of the gap, but it's a little bit more subtle. So in the MDC, the way the gap shows up is if you just had a single crossing in the MDC, you would just have a single energy where there's one peak, and then all the other energies would have two peaks. But instead, you have sort of an extended energy range where you have one peak. And this is sort of the gap region where nominally there should be no states there, but because of resolution and other factors, you do have states, and you can observe an MDC peak. So the main result of this paper was that the substrate, which is silicon carbide, breaks the sublattice symmetry of graphene, and it opens up a gap at the Dirac point. So it should be a crossing, but instead, because of the breaking of sublattice symmetry, there is a gap there. And this gap is most readily seen in the energy distribution curve because it is a gap that opens up as a function of energy. So here's another data, and these are for iron-based superconductors. And this was one of the first ARPES works on iron-based superconductors. And there are a number of aspects of this that I want to illustrate. So first of all, well, the color scales for the Fermi surface map and the high symmetry cuts are different. That's sometimes you use different color scales to highlight different aspects of the data. You'll notice that there are sort of different bright regions, so different light grays on top of the dark gray background. And this is the major strengths of the ARPES technique. So many materials of contemporary interest have multiple Fermi surfaces in different regions of the Brillouin zone, and you can sort of see what's going on each of those different Fermi surfaces directly. Another thing that I want to point out here is that if you look here at the X points, so the gamma, K, X, all of that, those are high symmetry points in the Brillouin zone. And also here at the M point, you can see that on either side of those spectra, you have different intensities, even though according to the theory, which is the red lines, you should have the same information there. So these different intensities on the two sides of the M point and the two sides of the X point are an example of matrix elements. So this is just an experimental fact that because of details of the experiment, you can have sort of the same band looking brighter in one region versus another region. And this is also, these data also show an illustration of sort of interaction between experiment and theory. So you can see here that there are theory data, theory lines overlaid on top of the data. There is pretty good agreement, and oftentimes ARPES experimentalists will collaborate with people who calculate band structure, who calculate energy versus momentum relations to sort of ascertain like what is happening in the material. Is it well captured by theory? Is there some information that theory can give us that helps us interpret the data better? And then, oops, and then the last piece of data that I want to cover is in strontium ruthenate. And I should probably update this slide because there has been more work done on this. But basically here what they did was a very detailed quantitative analysis of the energy versus momentum dispersion relation. And basically let's just focus on this panel over here. So the gray dots are basically the band position that is measured from the momentum distribution curve analysis. And then there is sort of the light gray line here is the band dispersion that is expected from a non-interacting model. So what interactions do is they make the slope of the dispersion smaller, they make the velocity smaller, and then and that is captured in the black line here, which is electron-electron interactions, giving the renormalization. And then on top of that, there's a bend that originates from electron phonon. So this is just an example of sort of very rich information that can arise just by looking at one band. And here, oh, sorry, that was not the last one. This is a charge density wave system where they quantified the charge density wave, and there's actually two different charge density waves onsetting at two different temperatures in this material. And they can quantify the gaps with ARPES and see different gaps opening up at different charge density wave temperatures that were previously identified with other techniques. And I just want to go through this quickly and end here with the slide about resources. So these are some resources of different degrees of technicality that give information about ARPES, and I'll be happy to provide more updated sources as well. I just want to highlight actually this third source, which is a very useful resource for me for learning about. So in the slides that preceded this, I mainly talked about momentum in the plane, but information about out of plane momentum, so the KZ direction, can be learned by varying the photon energy. And this third resource gives a really nice description of how to do that. And it's also a fairly short paper as compared to the other ones here. So that is something to look at. And this first source gives a sort of a more quantitative example of ARPES matrix elements that might be illustrative as well. Okay, so thank you for your attention, and I'll go ahead and stop here.